the first class is very important in any subject. You know, the first class is very important, right? Because I want to convey certain things that might not be repeated again, right? And first class is always important because it gives you a whole perspective of the subject, what books you should read, how you should follow your study, all such things. So coming back to that, uh, please note down certain things. Okay, before that I would like to say that today I am conducting this meeting over a desktop and in Ubuntu Linux because I want to show you something. That is my intent. And since I am in Ubuntu, I will not be able to use my old style of using a whiteboard and writing and jotting down things, right? Got my point? Because Ubuntu doesn't have the driver software for my Wacom digital device, so that's a problem. And if I want to put some annotations on PDFs, that I have to do with a mouse, so that's a very tough thing to do. So please bear with me because I am not habituated to teaching like this. I don't enjoy. I always enjoy a whiteboard based teaching. But still I want to show you something. That's why I have logged into Ubuntu. So this is point number 1. Point number 2, what book you are supposed to follow? Only one book you are supposed to follow as text, right? Yeah. Hello? Yes, somebody said something.
Yeah.
Hello? Hello? Am I audible?
Yes, sir. Yes, sir.
Yeah,
Yes,
yeah.
sir. Yes,
So
sir,
the
you are.
only book you should be following is the Dragon book. So the compiler book by Ullman, Shetty and Lamb is called the Dragon book, and you'll be happy to know that for this book, Professor Ullman got the Turing Award recently. Like the Turing Award is the most prestigious award for computer science. It's the Nobel Prize for computer science. So this book, I read this book, even my seniors read this book, and you are going to read this book. That is the standard textbook that you are going to follow. Now, what you are going to get in this book, if you have the book, you can open the book in a PDF. You can view that PDF in a separate window. I think you have that book. Basu has forwarded that PDF to all of you, right? Yes or no?
Yes, sir, I have forwarded it.
Yes, sir.
Yeah. Yeah. So open that PDF in a separate window. Just I want to say some points, salient points. Is it possible right now to open that book?
Yes, sir.
Yes, sir. Yes, sir.
Yeah, yeah. If it is possible, please open. Let me open that also. Let me open Basu's email. Did you open?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, that's fine. Give me some time. So if you can see, please go through the book. Those who have opened, I find myself in a very helpless situation. I have absolutely no control on what you are doing. So how many of you have opened the PDF? Okay, so if you can see chapter number 1, table of contents. You go to table of contents, page number Roman 9. So you have gone there?
Yes, sir.
Okay, that's good. So what you can see is chapter number 1, introduction. So it has many subsections in that chapter, right?
Yes,
So
sir.
I would ask you to go through chapter number 1. That means 38 pages within 1 week. This is assignment number 1. So I start the class with an assignment that you have to go through chapter number 1, that is 38 pages within 1 week, right? And as you can see, chapter number 1 in section 1.1, there is a precise on language processors. Section 1.2, it has a overall discussion on the structure of a compiler, evolution of programming languages, all such things. Chapter number 1 is extremely important, and that is why first class is always important, because I'm going to say you some more things. Now come to chapter number 2. If you come to chapter number 2, the name of the chapter is simple syntax directed translator, right? And you will find something like 2.4 parsing, 2.6 lexical analysis, 2.7 symbol tables, 2.8 intermediate code generation, right? And then 2.3 to 2.6 chapter section 2.6 is elaborated in chapter number 3 called lexical analysis. Now this chapter I will go very fast. So I will go chapter number 2 and chapter number 3. I will go very fast because chapter number 3 is a whole example of applying your concepts of regular expressions. You can see chapter number 3, lexical analysis. Now I will explain what are all these terms, what are all these terms that you are going through. So chapter number 3, lexical analysis, I will go very fast. I will try to write programs. I will try to give you a practical exposure to all your old concepts of regular expressions, right? So for example, if you go to 3 point if you go to 3.5, 3.6, 3.7, 3.8, you can see your known terms, right? Conversion of an NFA to a DFA using regular expressions for searching. You will use regular expressions for your lexical analyzer generator, all those things. Now come to chapter number 4. I'm moving fast because I don't have any option. Chapter number 4, syntax analysis. Now syntax analysis is a chapter that would deal with the structure of your programming language constructs and how they are slowly converted, how they are checked for their syntax, whether the program that you have written, the source code in a high level language that you have written, whether it conforms to some language structure, right? So you can see 4.2 context free grammars, 4.3 writing a grammar, 4.4 top down parsing, 4.5 bottom up parsing, 4.6 LR parsers, right? Now in 4.7 you will find LR bracket 1. In 4.7.4 you will find LALR. Some topics like this, right? So I would go through them very fast because I would have a presumption that I have taught grammars and regular expressions in great detail in the last semester. right? Yes or no?
Yes, sir. Yes, sir.
So
Yes, sir.
the thumb rule is this book should be your Bible. You should be having this book every time, whatever you do, whatever activity you do, studying, reading, anything, right? Now, so what is my job? So let me define my job. So I'll be teaching compilers, right? Now, so what are compilers basically? Can anybody define what are compilers?
So the
Anybody?
software interprets and
Yeah.
debugs the program.
Please speak bit louder. My headphone
Sir,
is not in a very.
sir, a software that interprets or and debugs the program, sir. Like points out the bugs, not debug rather, points out the bugs in a program.
So I would just change the definition a bit. I would not prefer to use the word translate right now. Yeah, I prefer to use the word translate, but I would not prefer to use the word debug right now. Okay, so compiler is a piece of software. What type of software? Any idea? Anybody? I want other peoples to interact. Only few people, like 4 to 5 people, interacted with me in my automata classes. Nobody else interacted. So my question is, how many types of softwares can you say? So specifically, there are two types of softwares, right? System software, application software. Agreed?
Yes, sir.
Yes.
Yes, sir.
Yes.
Yes,
So
sir.
compiler is a system software. First of all, compiler is a system software. Why? Because the job that the compiler does, what job a compiler does? The basic job is it translates from one programming language representation to another, right? So it's a translator of representations. Now let me refine the term representation. What I mean by representation, that you write a program in a high level language is the representation of your code in some high level language, right? And since you are students of 5th semester computer science, it's very trivial to repeat that the program that you write in a high level language is not the program that is worked out by your computer, right? Done. So that representation of your program that you write in your high level language, English like languages, with easy syntaxes, easy to understand, that's why we write programs in high level languages. That representation of that very program needs to be converted to a representation that your machine understands. Now what does your machine understand? Any
So
idea?
machine level language, sir.
Yeah, machine level language. Or more trivially, if I am supposed to take this class in a school, I would say that your machine understands zeros and ones, right? But since you are in computing class in 5th semester, a machine understands machine language. So is compiler is that system software that integrates with your system. Now by system I mean both the hardware and the software. Now compiler is a system software. By this definition I mean compiler can be treated as a software that very tightly integrates with your operating system, right? So that way it is a system software. Also, the compiler constructs the stages that the compiler goes through in translating your program representation in some high level language to some machine code needs to have the knowledge of the architecture of your machine also. It needs to have a, a one-to-one mapping of the assembly instructions that your CPU allows you to do. It needs to have a mapping of all the registers that your CPU has. Do you understand?
So
So compiler is a system software that integrates very tightly with your system architecture. By system architecture, I do mean the CPU and its registers only right now. I have nothing to do with the system bus. I have nothing to do with your motherboard. No, I am only concerned about the CPU, the registers, and that's why I would my next assignment should be that you should be downloading the Intel 64-bit architecture and assembly codes, the mnemonics found from Intel's original website. You go to Intel's original website and download the Intel instruction set. It is called the instruction set. So if you recollect from your microprocessor classes, every processor has the instruction set, right? Do you agree? Yes.
Yes, sir.
I hope you remember all such mnemonics like MOV, MVI, LTI, right? All such things. So each and every processor system has its instruction set, and at some point of time during the translation of a program from a high level language to the machine code, the compiler needs to have the complete knowledge of the instruction set of your CPU, and that knowledge is provided by the operating system to the compiler, right? So you can think of it as a trio: the operating system, the processor, and the compiler. It's a trio. It's a whole box. It's a very close example of very close integration of things. So what I mean by this is, so generally instruction set is independent of the operating system. So when you go to the Intel's website, you should be downloading the instruction set for Intel x86 architecture, right? 64-bit architecture. There you should not be specifying that, okay, I am downloading it for Linux. No, it is independent. On Intel you can run Windows, you can run Linux. So don't get confused by the fact that they are closely integrated. It doesn't mean that the instruction set is dependent on the operating system. No, the instruction set is independent. It is called ASM, the assembly format of addressing the registers and various modes of the CPU. But when you design your compiler version has something to do with the operating system, right? For example, if you use Turbo C runs on Windows. So next class when I'll be using my whiteboard, because I'll not be using Ubuntu in that class, I will draw pictures to show you how those interactions between the compiler and the instruction set is facilitated by the operating system. So operating system is a facilitator, right? It facilitates the understanding of the instruction set of the hardware by the compiler, and the reverse also. So that those three makes it a very closely coupled system. Compilers very closely coupled with the instruction set and the operating system, and that's why it's a system software. Done? Good, right? Okay.
Sir,
Now my next question is, um, you write source code in high level language, right? Now what are the things, why do you write code in a high level language? That is my next question.
excuse me, sir.
Yes, why
Sir,
do you
are
write
you
code? Yes, hello.
sir, are you trying to show something on your screen, sir?
No,
Because
I
you
am not trying to show something on my screen right now. So right now my screen is blank, right?
Yes, sir, you're not sharing anything.
Yeah, I'm not sharing anything. I'm sharing my voice. Is my voice reachable to you?
Yes, sir, yes.
Yeah. So I started the class with my with the statement that I would be working in Ubuntu to show you something, but yet now I have not started showing you something. Right. I'm just talking. Can you hear me? That would be enough.
Yes, sir.
Yeah. So I'm not sharing anything right now. Usually I don't use slides, you know that. Okay. So my next question, I am interacting with you right now. Okay. So my next question is, what are the characteristics of source code? Why do you write programs in high level languages?
Sir, easier to read, write, maintain.
So it's impractical to write it in assembly or something.
Yeah, both are right answers, but a easier answer is it matches our understanding of languages in how we speak, right?
Yes, sir.
We
More
have a
into
perception of we have a perception of a language structure in our brains, right? For example, when you talk with your family, you follow a structure, and that structure is a recursive structure again. Do you agree?
sir,
Hello?
sound is kind of buzzing.
So hello.
Yes, sir. Yes, sir.
Yeah. So that is what I mean by the perception of both written and spoken languages of humans. So we human have our own perception of a language, and programming languages are generally developed to match that notion or perception of languages that closely resembles human beings, right? So that we can get rid of all those zeros and ones complexities, right? Now, what is the immediate disadvantage of that? Any idea?
So machines don't understand our language and our
No,
patterns.
I'm not asking about that disadvantage. I am asking about the disadvantage that comes out directly if you try to implement a programming language that matches our perception of language speaking and writing. Don't go to machine language right now. I am talking about high level languages. So we develop high level languages uh, to closely match the perception of writing and speaking skills, right? So that we can write something, we can write code. um, for example, scanf, printf, all these terms are in very close proximity with the English language that we write, right? And you have studied solving mathematical problems from your schools, and based on that structure, your programming structure of functions, for example, function calls are designed, right? Now, what is the immediate disadvantage of that? So one immediate disadvantage is redundancy. Do you agree? So to try to make things simple for us, so that we can understand what we are writing, we we generally induce or introduce much redundancy. That is a very important point of concern, right? So compilers also does that. So um, let me show you something. Okay. Let me show you something.
Sir, could you repeat what the disadvantage of an HLL of a high level
So
language is?
the direct disadvantage, there are many disadvantages, right? But
Yes,
since it is a we are starting the class today, I would say that the direct disadvantage that you have in your pursuance of trying to make the programming language look very similar to our habitual way of talking and writing, we generally induce or introduce redundancies. Now those redundancies are uh, needs to be taken care of, and that taking care of redundancies, so that the meaning is not lost, but the program looks compact, the program looks unambiguous, right? The program doesn't lose its structure, but the redundancy should be removed, and that is what is mainly known as optimization, right? Now let me show you a picture. Okay, so what slides you are going to follow? Uh, there you can follow. Take a note. You can follow the slides of say um, the slides of Ame Karkare. from IIT Kanpur. Just take a note. AMEY. Am I audible?
Yes, sir.
Yeah.
So will we find these online, right?
Yeah. I'll be sending the link. Will that do?
Oh, yeah, thank you.
Yeah, I'm sending the link right now. Yeah. So the basic functions of a compiler. Let me share my screen.
Sir, can you give an example of redundancy?
I'm showing the screen. One minute. I'm not finding the sharing option. Why? The sharing option is there, right there only, right?
Yes, sir. Yes, sir. Right
Yes, sir.
beside the
We,
microphone.
Yeah,
right beside
right.
the microphone.
Yeah, but can you see my?
Yes, sir. We can see your screen.
You
Yes,
can
sir.
see the
Visible.
screen, right? Yes. Can you see this screen?
Yes,
Yes.
sir. Yes, sir.
Yeah. So, so this is how this is the basic structure. Now, Basu, tell me how much time do I have?
Sir, 15 minutes.
Okay, that's fantastic. So this is the see what I want to say is this is the basic structure of a compiler, right? So if you follow my mouse pointer, can you see my mouse pointer?
Yes, sir.
So this is the compiler. You write a program in an editor, you feed the source program in a compiler, the compiler compiles your program, right? So the source program is being converted to assembly code, right? Now you should be asking me, why not machine code? Why assembly code? Because this assembly code is taken care of by another part of the compiler. Now there are two schools of thoughts. Listen to me very carefully. One school of thought says that assembler is not a part and parcel of the compiler system, and another school of thought says that compiler is a collection of the compiler itself that converts the source program to assembly code. That means the machine independent code, the assembly code, right? And then the assembler converts that assembly language code to the particular instructions of your CPU, that is called machine code. And that code is linker is a piece of software that resolves different portions of machine codes. And then loader is another piece of system software. So compiler, assembler, linker, loader, these are all system softwares, right? And you find the executable image, right? Can you see this picture?
Yes, sir.
Yes. Does it make sense?
Yes, sir.
So we are going to read. So what we are going to study? We are going to study specifically this portion, compiler. How the source program is a source program. For example, you write a program in C. How it is converted to assembly code, right? And how the assembler converts that assembly code. Generally, assembly code is machine independent, right? How that assembly code is translated to the machine dependent machine code. So the assembler needs to have a precise knowledge of the instruction set of your CPU, right? and then you have the linker, you have the loader. Got it? Now, you can talk about debugger at the latest stage. Somebody was talking about debugger. So what is a debugger? It debugs errors, right? It debugs what went wrong. So you write the program in an editor, feed the program to a compiler, you generate assembly code, the assembler code takes the assembly code as input and outputs the machine code, and then you can have actually this machine code is you can have multiple machine codes for huge programs. I will show you examples. Then the linker links all those machine codes that are required, and then it prepares the final machine code. Then you have the loader, and the loader you generate the executable machine execution for the target machine, and errors are fed back to the debugger and you debug. So debugging is a very runtime thing, right? Now, can you name a very popular compiler that you have used?
GCC compiler.
What is the full form of GCC?
So the new compiler collection.
GNU
Compiler collection.
compiler collection. Why it is called collection?
So because the GCC can be used to compile source code of many languages.
Yeah, this is answer number 1. Answer number 2 is GCC is usually implementing the compiler itself, the assembler, and the linker, all three. Right? That is another reason of calling it a collection. So GCC views things as a compact thing. So compiler, assembler, linker. Right? Okay, so this is the complete picture of your compilation process at a very abstract level. I have not started going into details. So we are going to study the phases of this compilation process, how the source program is slowly converted to assembly. This is the main portion, right? And then you pick up the assembler for your x86 architecture, and then you input this machine independent assembly code. It will generate the machine code for your architecture, right? And then you have independent linker program. GCC has all these three integrated, and that's the power of GCC. It just calls the compiler, then it calls the assembler, and it calls the linker. GDB, the debugger, the very popular debugger for the GNU platforms. So let's not call GNU, let's call GNU, right? It is pronounced as GNU, right? So like GCC, there's a very popular debugger called GDB. So you can execute your program, and then at runtime you can debug and push the debugging results. Based on your debugging results, you can do some correction of your code and try to make your code better. So this portion is the human portion, right? And this portion is the machine portion. This is how it happens. So what we are going to study? We are going to study from that book so many chapters, so many sub chapters. We are going to specifically study the science behind the design of algorithms of conversion of a source program to assembly code. Parallelly, not like the previous semester, we are going to see things visually, how things happen. Got my point? For example, let me come back to this. This is the reason I am on Ubuntu right now. So, Basu, I think I will have 10 minutes of time, right? Yes?
Yes, sir.
Hello?
Yes, sir.
Yeah,
Yes,
yeah.
sir.
Yeah. So let me use all free software things. Like I'll be. Is my screen visible?
Yes, sir.
Yes, sir.
So let me write a program, right? test program dot c. Let us write a test program. I will write a very simple test program. I will keep three things in mind. What are the things? First of all, I would include header files. Then I would use a macro, because we know that the very first step of converting your high level language to machine code is you need to pre-process your code, right? So all your macros and all your hash includes should be taken care of by the pre-processing stage. How many of you know this? Yes or no?
Yes, sir.
Yes. So to show you how pre-processing works, I would be using, say, hash include and write a very simple program, right? And then I would use I would use header files, I would use macros, and then I would use function calls. And additionally, to show you what are library functions, I would use mathematical function, right? uh, Say for example the sine function, the cos function, so that I can use the macro definition of, say, pi, a very interesting and most commonly used, very loved by mathematicians, right? So I include math.h, and then I define pi. So what value should I keep? Yes, Basu?
Yes, sir.
Yes, pi. I'm keeping pi to be 3.141, right? I'm
Yes,
not
sir.
complicating things. So main. So it's always a good practice to use the return type so that you can debug. So the reason that I'm writing int main is I expect to have a return value in my system after my program exists, so that I can I can perform debugging, right? So I have a printf call. Then for example I want to print sine of pi, so I'm calling the macro and I'm printing it in float format, right? And that's it. Now the integer that I am using to get the return codes, for that I would be using exit 0 to end my program, right? So that the code is generated and returned to the system. Done? Yes or no? So this is
Yes.
the program, right? So test program.c, save test program.c. So this is the program, right? Okay. Now let me show you um, how to compile the program. How to compile the program in GCC? Any idea? You have written programs in GCC?
Yes, sir. We write it G plus plus. We
Let
start
us
with.
use GCC.
Okay.
GCC because it's a C program, right?
Yes, sir.
Yes. Then tell me how to
Yeah,
compile
like
and execute test program.c.
So name of the program, GCC.
Yes.
So this
GCC
what
hyphen O
Yeah.
test prog, right?
yes, sir.
Test prog.c, right? So I forgot to put the semicolon, right? So compiler, one of the important features of compiler is it immediately gives you such errors, right? Okay, so you got some warnings. What are those warnings? Can anybody debug it for me?
So you wrote print instead of printf.
Yes.
Printf. We have to
Yeah.
use printf, sir.
Yeah. I have used printf.
No, no, so you
No,
wrote
sir.
print.
Print.
Oh, okay, okay, okay. I typing error. Okay.
And
Yes.
and so probably we
Yes.
should have used return
So
instead
we
of
have to
exit.
use
So
so we
Yeah.
have to use lib.h for the exit function. We
Is
have
it?
used yes sir.
See the last line. Can you see the last line? It says um, it says that you have included math.h. So let me try something like linking the math library. Yes. So it's a warning, right? stdlib.h. Let us give it. Is it okay right now? So no warnings, clean compilation, right? And let us check if I don't give -lm, it's also a clean compilation. So just note the version of GCC. It doesn't require it doesn't so version 9.3.0 doesn't require the math library to be statically linked. A simple compilation is done. Now I want to show you something. So what are the steps what are the steps that it follows your program. So your program has includes, it has defines. So your preprocessor should be doing such things, and then the pre-processed output should be taken in by the real compiler to convert it to your assembly, and then the assembly code is the assembler is going to convert that code to your object file, right? Is it? So there is I can put some options to show you that to show you the temporary files that are being output in all these temporary stages. So I will just save the temporary files, temporary steps, and output in verbose mode, and then I would compile. Okay, can you see this?
Yes, sir.
Yes,
Yes, sir.
yes or no? Yes. Okay.
Yes, sir.
So what I have done is I have um, I have saved the temporary stages of the compilation process. Now let us see what we have in the directory. So we have the executable test prog, we have the test program.c, and we have additional three programs: test program.i, that means the output after the pre-processing stage; test program.s, that means the output after the compilation phase, the assembly; and this is test program.o, that means the output of the assembler itself, right? Is it okay? Now let us go through this output, because we have put it in verbose mode, so I can show you. By the way, are you viewing things on a computer, or you are viewing things
it's on a computer, sir.
on a phone? Huh?
Computer, sir.
Computer?
Computers.
Okay, that's good. So up to this, it is of no importance, because it talks about the several options with which GCC had been configured, including the GCC version, right? Okay. Now this is the first call to a program called CC1. This is the path of CC1. What is CC1? CC1 is a program, right? Now what is that program? Any idea? CC1. What is CC1? Any idea?
Compiler.
Yes. It's a real compiler, right?
Yes.
Yes, it is. It is the real compiler. So this you what you do is you call this compiler CC1 with these arguments and ask the compiler to produce testprogram.i. That means you call CC1 with these arguments. I'm just highlighting the arguments and ask CC1, that means the compiler, to act as a preprocessor and convert the .c to testprogram.i. So this is the whole usage of the first call to CC1. Is it visible?
So what is testprog.i exactly?
What?
What is testprog.i?
I will show you. Please wait. Testprogram.i is the preprocessed output. So your input was testprogram.c and the preprocessor is called the preprocessor. What is the job of the preprocessor? What does it do? It appends all the hash includes .h files to your source file, point number one, and it creates an environment where all your macros will be replaced with the values. So whenever I have capital pi in my program, it will be directly replaced with 3.141. So these are the two distinct works of the preprocessor. Agreed? Yes or no?
Yes, sir.
Yes, sir.
Yes. So testprogram.i. Actually, this is a very good question, but for that I need to go out of this and show you what is testprogram.i. So this is testprogram.i. This is testprogram.i, right? So it uh, it actually um, it actually creates an environment where all the required .h files should be appended, where all the types should be taken care of. So unsigned char is actually, it is type def to underscore u underscore char, right? So all these things are taken care of. And this is your preprocessed output. So after taking care of all your type checkings, all your hash includes, all your hash defs, that means hash defines, this is .i, and this .i is then fed to the compiler to generate .s. Got my point? Yes or no? This is how the .i looks. Okay, so want to see how .s looks? Now, is it similar to the assembly language programs that you wrote?
Yes, sir.
Yeah. Can you remember all these things?
Yes,
Yes,
sir.
sir.
It is similar
Yes. Yeah.
in MIPS.
It's not only similar, it is exactly the same, right?
Oh, yes, sir.
Right? Okay. So let me show you what is testprogram.o. Can you understand anything?
No, sir.
No,
So why
sir.
don't you understand? Why don't you understand?
It's the same
Because
thing repeating over
we are
and over.
trying to open machine code with a text editor. A text editor is basically ASCII editor, right? And this machine code is in 0 and 1s. Often these 0 and 1s are written in terms of hex codes. So you need a hex dumper to dump this code and get the hex values of your machine code, and still then you would not understand anything, because this is not destined for your understanding. This is destined for the understanding of your machine. Agreed?
Yes, sir.
Yes or
Yes.
no? So
Yes,
you
sir.
started with, see, you started with testprogram.c, and since I saved the temporary actions of the compiler, the testprogram.c was your C program. It was first converted to testprogram.i after being preprocessed. That preprocessed code is inputted to the compiler, and the compiler generates testprogram.s, and then the assembler is called. The assembler generates takes testprogram.s as input and generates testprogram.o as output. And then the linker is called. The linker links many such .o programs and generates test. This is the executable, right? So let me execute /testprog. So value of sine pi is this, right? I have executed. Let us see once more. So we started with testprogram.c. Then we call the preprocessor. You took care of all the hash includes, all the type depths, and all the hash defines, and generated testprogram.i. Then the real compiler comes into play. The real compiler means all those chapters that I was talking about in the book, right? We'll go through all those chapters. We'll generate regular expressions. We'll generate trees. We'll substitute values. We'll do everything. Don't worry.
Sir,
First class is, yes.
so actually attendance also started in the other class, sir.
It other class.
Yes,
Okay,
sir.
just give me 2 minutes of time. I will continue with the same thing in the next class, right? Just give me 2 minutes. So we started with testprogram.i. The preprocessor is called, and you have the testprogram.i. And then the real compiler acts on this testprogram.i to generate testprogram.s, the assembly code. Then the linker is called, and the linker links, the assembler is called. The assembler takes .s as input and generates the object file that we don't understand. At most, we can have a hex editor to dump the hex codes, right? But that is of no use to us. And that is why we are writing programs in high level languages. And then the linker is called, that links many such .o files to build test program. And that is your executable, right? Just let me show you, just 2 minutes. So first of all, this was called, the compiler was called, and testprogram.i was built. And then the compiler was again called in this line, and testprogram.i was taken as input, and testprogram.s was the output. This is testprogram.s. And then you call the assembler, right? So this is the assembler. AS is the assembler program. The assembler program takes .s as input and gives you .o as output. And then you call the linker. It's a program called collect2. This is the linker. The linker is being called, and it outputs testprog for this x86 64-bit architecture, right? So what I've done today I have shown you how we can use the flexibility of GCC for a very good understanding of what happens inside your GCC, right? And I will go with more deliberation in the next class. Thank you very much.
Thank you, sir.
Yeah.
Thank you, sir.
Thank
Yeah.
you, sir.
Thank you,
Any
sir.
questions, you may put me emails, right?
Yes.
Yes.
Yeah.